Hello and welcome to the video presentation of the final project of Higher Diploma in Science in Computing course, Software Development Stream. My name is Jacek Smoleń, student ID X17157765, and I will have the pleasure of walking you through a Pong video game clone created in Unreal Engine 4. It is estimated that 2.3 billion gamers across the globe will spend around $140 billion on games in 2018. Considering that global games market revenues were 70.6 billion in 2012 and maintained double-digit growth since then is truly remarkable. Game engines such as Unreal Engine 4 or Unity have bridged the gap between AAA game development studios and one-man indie game developers by lowering the entry level to entering the market, both skill-wise and financially. With Unreal Engine 4 being free and charging only 5% of the game revenue after a certain threshold, together with over 5 million in grants for developers, creating a video game using this powerful framework is a viable business idea. Competitive multiplayer games stand out. As of today, 5 out of 10 top games by player count on Steam are strictly competitive multiplayer games, where players compete against other players. The choice was made to recreate 1972 Atari's Pong video game because it is one of the earliest competitive two-player games ever developed and is considered the game that launched the video game industry as a lucrative enterprise. Pong definitely shaped the video game market as we see it today and marked the start of a new entertainment medium. This project is a homage to the game that started it all. Its goal? Develop a game with gameplay mechanics as close to the original experience as possible, with no bugs or glitches and smooth gameplay. Considering that Unreal Engine 4 is one of the most advanced game engines available to date, the idea proved to be a challenging task, but also very satisfying when done right. Unreal Engine 4 is a suite of integrated tools for game developers to design and build games, simulations and visualizations, first showcased in the 1998 first-person shooter game Unreal. Although primarily developed for first-person shooters, it has been successfully used in a variety of other genres, including stealth, fighting games, MMORPGs, and other RPGs. With its code written in C++, the Unreal Engine features a high degree of portability and is a tool used by many game developers today, with it being source available. The most recent version is Unreal Engine 4, which was released to the public in 2014. The whole game was developed using Blueprint's visual scripting system in Unreal Engine 4, version 4.20.3. The Blueprint's visual scripting system in the Unreal Engine is a complete gameplay scripting system based on the concept of using a node-based interface to create gameplay elements from within Unreal Editor. As with many common scripting languages, it is used to define object-oriented classes or objects in the engine. This system is extremely flexible and powerful as it provides the ability for designers to use virtually the full range of concepts and tools generally only available to programmers. In addition, Blueprint-specific markup available in Unreal's Engine C++ implementation enables programmers to create baseline systems that can be extended by designers. Testing consisted of internal and external testing. Internal testing took place throughout the whole implementation phase, and external testing commenced once the required game functionality was finished and internal testing gave satisfactory results. Internal testing was pretty straightforward. After a chunk of the game was implemented, it was run directly in the viewport of Unreal Engine, and functionality that was implemented was tested. About halfway through the implementation, regression testing was introduced. It was carried out by checking a set of conditions on top of testing introduced functionality. The set of conditions is as follows. 1. Ball hits left paddle. 2. ball hits right paddle. 3. Ball hits top horizontal border. 4. Ball hits bottom horizontal border. 5. Player 1 scores. 6. Player 2 scores. 7. Player 1 wins. 8. Player 2 wins. While those scenarios occurred, the tester made sure that all game elements run as expected. The score updates, the intro screen is displayed, the game ends, etc. Same regression testing took place when a bug or a glitch was fixed, or when the game parameters were adjusted. The game was also tested in terms of gameplay. An effort was made for the game to resemble the original Pong game, and ball speed, paddle speed were adjusted and tested until a satisfactory level was reached. Once the game was developed and internal testing was completed, external testing began. External testing consisted of packaging the project for different platforms and distributing it among friends and colleagues for playtesting. After playing the game, participants provided valuable feedback, and adjustments to the game were made based on it. External testing ensured that the gameplay is pleasant, challenging enough for experienced players, but at the same time not too difficult for new players. In order to achieve the original gameplay mechanics, a YouTube video presenting original 1972 Pong game was analyzed and then implemented using modern tools. The level layout was referenced off of a Pong Wikipedia page, image depicting black screen with paddles, middle line, the ball and scores. The Wikipedia image was applied to the surface in Unreal Engine editor. It supplied a reference and made sure that all assets that are created are in scale and placed in correct distances to one another. Static meshes were created for each object. A ball, a paddle, a border, and a dashed line. As the borders in original game were invisible, reflective materials was only applied to the dashed line, paddle, and the ball. Borders were left with a default material, which was invisible to the player. After studying the original gameplay video, we can see that when the ball reaches left or right player's goal, it disappears. That piece of functionality was implemented by adding a shade next to the goals. Also, 2 text render actors were implemented to keep the score. In original Pong game, the paddles were controlled by analog dials that allowed for quite precise paddle control. In our case, it could be emulated with mouse input, but that would put the second player at a disadvantage of using the keyboard. That's why a decision was made to assign controls of both paddles to the keyboard. That caused a problem with controlling the paddle in direct way. Due to the game's fast pace, the player is required to move paddle around quickly. In original Pong game, player controlled paddle position directly, as in his input directly changes the paddle position. It is fine when analog controller is used, but when binary controller like keyboard is used, it makes positioning the paddle in a precise manner impossible. The problem was solved by making the player control the force exerted on the paddle rather than position directly. It led to a smoother paddle movement and a little bit of inertia, allowing for more precise paddle movement and better feel in general. Furthermore, a limit was set how far the paddle can travel. Looking back at the original Pong game, the paddle movement was limited by bottom horizontal border and about 1/20th lower than the top horizontal border. After investigating, it was found that such limitation was a conscious decision of game developers. The game was aimed at the arcade and making a random situation in which it was impossible for the player to hit the ball with the paddle made sure that the game ended and players didn't play indefinitely. After investigating the reference video, a set of rules was extrapolated from it. 1. Angle of incidence is equal to the angle of deflection on borders. 2. At the start of each round, the ball is launched at a random angle at the player who lost previous round. 3. When the ball collides with the paddle, the angle at which the ball is deflected is dependent on which part of the paddle the ball made contact with. The further to the edge of the paddle we go, the steeper angle of deflection. 4. The ball speed changes. We can clearly see in the video that when the ball is hit with the middle part of the paddle and flies straight, it slows down. After further analysis, it turned out that when the ball hits the paddles, its horizontal velocity component doesn't change and paddle hits affect only the vertical velocity component. There were 3 sounds used in the original game. 1. Ball hitting a border. 2. Ball hitting a paddle. 3. Player scores or ball hitting a goal. The sounds were copied from the original video and implemented within the game. Scoring occurs when player fails to hit the ball with paddle and the ball reaches a goal. When player scores, a couple of things occur. The score number is updated, a sound is played, and the game freezes for about 2 seconds. Only after those actions, the ball is launched at the player who let the ball reach his goal. The game ends when one of the players reaches 11 points. When player scores and wins the game, the level instantly changes to the intro level where score of the previous game is displayed. Paddles are removed and the ball is simply bouncing around the level until a coin is inserted and another game is started. In my implementation, I have added controls and project description, as intro level is the first thing a player sees when the executable is run. The biggest project-related challenge was to actually learn how to use Unreal Engine 4. At the beginning of the project, I was planning to develop the game using only C++. An effort was made to learn the language. Udemy classes turned out to be a very effective way to do it. However, on initial implementation attempts, the added complexity of Unreal Engine 4 made the approach unrealistic in the time frame available. A change in approach was made mid-project and blueprints were utilized, which in turn allowed to finish the game in time. One of the biggest implementation challenge was to get the ball deflection angle right. Problem came from a too experimental approach at the beginning of implementation phase. Instead of maintaining good programming practices from the start, priority was put on speed of development. That resulted in a very rigid code which made fine-tuning of gameplay elements like paddle deflection very difficult. Solution was found in recreating blueprints with good programming practices, where, for example, ball velocity wasn't a magic number, that is hard-coded integer, but instead was promoted to a variable that was used where needed and could be easily adjusted without sifting through the code. Another challenge I faced was to display previous game score on the intro screen. As intro level and main level are 2 separate maps, all the instances of main level elements were destroyed along with score variables upon closing the level. I needed an element that could be persistent all the time the game is running to transform score data from main level to intro level. Solution to this problem turned out to be a game instance blueprint. Okay, this is a walkthrough of the blueprints, some of the functionality. So, as mentioned before, the transferring of the player score was done by a game instance. This is game instance blueprint, and it just holds variables there, and there is no functionality attached to it per se. But let's go and see how it is actually transferred, the score from main level to intro level. Here we see main level and intro level. We won't save it. So in main level we're using this blueprint here, which is actually shown here. Blueprint ball. And in here we have our functionality. So what we wanted to see is what happens when one of the players scores and the condition is met. So the score is greater than 10, which means when it's 11, this condition will be true. Game over boolean will be set to true. And we're going to proceed to this. Cast to game instance, it just pulls out the game instance for us so we can operate on it. And we're setting the P1 score on the my game instance blueprint. And we're setting them from player 1 score from this instance, which then is killed after the new level is opened. Okay, now we'll go to a new level, which is intro, as you can see. And in blueprints, here we're using different blueprint for ball. It's ball intro, this one. And if we open it, we can see that at the begin play, so when this blueprint is triggered, we set the ball linear velocity, and then we cast to my game instance again, and we set the value P1 score. That's from the game instance, because that's the target we're using. And we're setting a value to our text render component. That is pulled out here. Get all actor of class text render. That's basically we're getting all of the text render actors. And if their tag P1 score tag and P2 score tag, that's for player 1, player 2. If they're true, we will set the text. And text is, we convert here the value, the integer, to text, and we set the text that get displayed here. That's basically it. I can go through the paddle movement as well. Paddle movement is basically we use force for paddle movement. So here we get the controls. The move _1 is basically W and S keys, and they control the axis. So they get the value from -1 to 1. If nothing is pressed, it's 0. It is multiplied by 100. And then we're making a vector where we change X, because the paddle only moves in X direction, which is top to bottom. And we add force to mesh, a paddle mesh, which is this component here. We can go over here, and here we see our paddle and the collision box around it that allows us to make this functionality of a ball bouncing off of the paddle. And the ball bounces off the paddle by making a cast on an event actor begin overlap. That is what the collision is for. We cast to different objects. We check if it's a paddle pawn left. If not, we check if it's paddle pawn right. If not, we check if it's a horizontal border. And depending on what we hit, we trigger different functionality. We play a sound. We get linear velocity of the ball to transform it. We transform it, basically reverse the y-axis, which is left and right. And we create the x-axis velocity depending on where our paddle is and where our ball is. So that's how we make the paddle deflect the ball at an angle. Okay, we can go through one more element. let's check the level blueprint for main level, and we'll go into blueprints, open level blueprint. Here we set the camera when we begin play, so when the level is opened we set up the camera and we get player controller. That's basically to set the camera of the player that is starting the level. That's how we do it, to set the camera, because usually in games the camera follows the player, and here the camera is static, so we're using this camera actor, which is actually here on the map, and we can see what it says. When we move it around, it will change orientation. If we move it up, down, zoom out, actually zooming out and in doesn't do anything because we're in orthographic mode, so that's it. It looks like a 2D game. We can change ortho width here, and that's basically it. Thank you.